Namaste, welcome back to the Pragna channel. You are watching Machine Learning Basics Theory playlist, and this is our sixth video in this playlist so far. If you haven't watched the others, go ahead and watch them if you want to learn machine learning basics. And today's topic is neural networks, and I don't think you need an explanation of what this is because everybody knows about neural networks, and our brain is an example of neural networks. This is a computational model and inspired by, guess what? I just said everybody knows why. Because our brain, it is inspired. This computational model is inspired by the way our biological neural networks of the brain work. Yes, you heard me correct. Based on the neural network in our brain, they designed this computational model. This one consists of interconnected layer of nodes, and they call them neurons. Yes, even in our brains we have neurons. They actually, copied it. Maybe God should sue these people, whoever came with us, because they didn't take his permission. This interconnected layers of nodes, and they are called what? Neurons, that process input data and learn to perform tasks such as classification, regression, pattern recognition, and more. Neural networks are a foundational technology in deep learning, a subset of machine learning. Okay, you have machine learning, then you have something called deep learning. So this is neural networks is the foundation of deep learning. Now let's learn about components of neural networks, or I would say key components of neural network. And we already discussed neurons are going to be there, but what is this? This is the basic unit of a neural network. Each neuron receives input, processes it using a mathematical function, and passes the output to the next layer. Okay, simple, correct? It receives input, processes it using a mathematical function, then it passes the output to the next layer. And we said next layer, we didn't exactly say what kind of layer because there are multiple layers. And that's what our next component is. What? Input layer, hidden layer, output layer. Input layer is the layer where the input data is fed into the network. Hidden layers are layers between the input and output layers where the network learns to transform the input into something the output layer can use. The network can have one or multiple hidden layers depending on what kind of transformations you want to do. So think of layer 1, which is the input layer, because the data is fed to this layer. Then you have plenty of hidden layers, H1, H2, H3, which does transformations, and this is sent to output layer. Now finally you have the output layer. This is the final layer that produces the network's output, which can be a prediction, classification, etc. Depends on what kind of functions you are giving neurons. And then another component is weights. What exactly it is? Connections between neurons that determine the strength of influence one neuron on another. Remember, we have discussed about weights in one of the algorithm. Do you remember which one it was? The linear learner algorithm. There we spoke about weights, giving weights to different features. Remember, because not all features will have the same weight. Some might have more, like the real estate pricing example we discussed there. Of course, the location is going to have higher weight than comparing with let's say the number of bedrooms or whatever it is. Yes, the number of bedrooms will have a weight, but not as much compared with the location. So even here, the connections between the neurons that determine these weights are the connections between the neurons that determine the strength of influence of one neuron on another. During training, the network adjusts these weights to improve its prediction. Similarly, there the weights were automatically improved. Here also, the network adjusts these weights to improve its predictions. And then you have something called activation function. This is a mathematical function. There are different different activation functions applied to the output of each neuron to introduce non-linearity into the model, enabling it to learn complex patterns. Common activation functions include ReLU, or rectified linear unit. Sigmoid, we heard about sigmoid in linear learner, and then something called tan H. And then finally, bias. This is an additional parameter in each neuron that helps the network make more accurate predictions by allowing it to shift the activation functions. Even bias we learned in the linear learner. And what was the bias? It's the intercept. If you know y is equal to mx plus c, right? C is the intercept. Same thing here. That's this one. So basically, these are some key components. So if somebody mentions neural networks, now you don't have to be afraid. You know what are the key components and how they are used. Okay, now let's learn how neural networks actually works. So the first one you need to learn is forward propagation. Okay, what is forward propagation? Here, the input data is passed through the input layer. Okay, you have input data and it is passed through the input layer in the forward propagation. And here each neuron processes the input by multiplying it by the neuron's weight. Okay, remember in the linear learner, how did we calculate the price? We had the weight and then the feature, and then we weight 2, feature 2, and then at the end we added the bias. Correct? Similarly, even here you are going to multiply the neurons weight. Let's say neurons, you are going to multiply neurons weight, then you will add the bias and applying activation function to process an output. This process continues layer by layer until the data reaches the output layer where the final prediction or classification is made. Basically, that's all happens in the forward propagation. Then you have backward propagation. After the network makes a prediction, you will have an error or difference between the predicted output and the actual target. Remember, even that price we had, if the actual price was this, the predicted price was this. Now you have an error of $5,000, correct? So backward propagation is here. After it made the prediction of this one, this error or difference being predicted is calculated. Now the network, it then adjusts the weights and biases in the reverse direction through a process called backward propagation using an optimization algorithm. And an example of that would be gradient descent. Okay, so why do you want to do this? Because to reduce this error, it does this something called backward propagation. This process is again repeated over many iterations. And these many iterations are called epochs, or I don't know how you want to pronounce it, but I would say epoch, until the network's prediction improves. So now you will do it again and again. Obviously the number of epochs is going to cause you the time and the processing power. So it depends on how much you want. If you want it to predict until this one is like around 1000, then it has to do many number of iterations, etc. Now the network is trained on a data set where the correct outputs are known. Over time, the network learns to minimize the error by adjusting the weights and biases, improving its performance on unseen data. So that's about it. Neural networks. You mastered neural networks now? Of course not. This is just to give you an understanding, because I heard so many people, they want to learn machine learning, but they are like, oh my god, I don't know anything about statistics, I don't know about so many concepts. They just get scared of machine learning. Of course, if you don't have right resources that explains you easily, right, you get scared. Even if I pick up a machine learning book and read it, I will get scared because they will have all these scary words. Even we are seeing them: gradient descent, epoch, and then we have seen that LDA, PCA, and whatnot. When you hear those words, of course you are going to get scared. But now let me tell me in the comments that so far whatever you learned in neural networks in these slides, is it too scary? Of course not. When you learn, you know that it is okay, that's it. But again, this is not you are not an expert, you are just still in the beginner level. But at least now if somebody asks how what are the key components of neural network and how neural network works. You know that you can tell somebody that, well, it will have a forward propagation where you are going to get your input data passed through the input layer. Then each neuron processes the input by multiplying the neurons weight, adding bias, and applying activation function to produce an output. And this process continues layer by layer until the data reaches output layer where the final prediction is made. And then you can tell them that there will be also a backward propagation and etc. Correct? So now we know how it works. Let's go through the examples. Image classification. We have already learned or used other algorithms to do image classification, but here we are going to learn how neural networks is going to help with that. Our example scenario, this one would be identifying objects in images. For example, recognizing cats versus dogs. A neural network is trained on a large data set of labeled images. So images of cats and dogs. The network learns to identify patterns in the pixels that correspond to each class. Once trained, it can classify new images as either a cat or a dog. So the outcome is automated image classification used in applications. Actually, this neural networks is actually used in Google Photos, where the software can automatically categorize images. And another example, speech recognition. An example would be converting spoken language into text via voice typing. A neural network is trained on audio recordings paired with their corresponding text. The network learns to map audio signals to phonemes, which are basic units of sound, and then to words. After training, it can transcribe spoken words into text in real time. And applications like Siri, Alexa, Google Assistant use speech recognition to understand and respond to voice commands. So behind the scenes, they actually use neural networks. And predictive maintenance, predicting equipment failure in manufacturing plants. These are some examples that we have also seen in other algorithms. Sure, many of these algorithms can, be used for different scenarios. A neural network is trained on historical sensor data from machinery along with data on past failures. The network learns to recognize patterns that precede a failure. It can then predict when a piece of equipment is likely to fail, allowing for maintenance before a breakdown occurs. Outcome: reduced downtime and maintenance costs as issues are addressed before they cause major problems. And then NLP, and we have seen the customer reviews in the LDA. Remember that? So sentiment analysis of customer reviews. Neural network is trained on text data labeled with sentiment, positive, negative, and neural. Remember, all these places we are giving it, it's like supervised, right? We are giving it data that is already labeled. In LDA, we didn't give it any labeled data. The network learns to recognize patterns in word usage, sentence structure, and context that indicate sentiment. After training, it can analyze new text and predict the sentiment expressed. Outcome: companies can use sentiment analysis to gauge customer satisfaction and identify areas for improvement. And final example, autonomous vehicles, self-driving cars. If you haven't sat in one of those, I would recommend you to do that. It's a scary experience, but scary good experience. Neural networks process data from cameras and something called LiDAR, and then radar and other sensors on the vehicle to understand the environment, recognize objects, and make driving decisions. The network is trained on vast amounts of driving data to learn how to navigate various road conditions and situations. Autonomous vehicles can drive safely and navigate complex environments, reducing the need for human intervention. So that's the outcome of this one. So there are plenty of examples. Most of them you might already being used in your real life. So what are the advantages of using this? The ability to learn complex patterns. Yes, neural networks can learn and model complex relationships between inputs, outputs, making them powerful for tasks like image recognition, language processing, and more. And the flexibility. Neural networks can be applied to a wide range of problems across different domains, from computer vision to finance. And scalability. Neural networks, especially deep neural networks, can handle large data sets and complex tasks, improving their performance with more data, like self-driving cars. How, you cannot get more complex data than that one. And considerations when using neural networks? Well, we have already seen that training data. Neural networks require large amounts of data for effective training. The quality and quantity of data significantly impacts the model's performance. And computational resources. Training deep neural networks can be computationally intensive, requiring powerful hardware like GPUs or specialized processors. And interpretability. Neural networks, especially deep networks, are often considered black boxes because their decision-making process is not easily interpretable. This can be a drawback in applications where understanding the rationale behind predictions is very important. So that's about it. And now it's time for our scenario-based explanation. Are you ready? And I'm going to pick our favorite example of image classification. Imagine you are developing a system to automatically classify images of animals into categories such as cats, dogs, and birds. The goal is to train a neural network that can make an image as input, take an image as input, and predict the correct category. Like if you give a image of cat, it should tell it is a cat. Now let's see how we analyze this using neural network. First, let's understand the problem. And what is our objective? Classify images of animals into predefined categories. And this is a supervised learning problem because network will learn from labeled data. Neural network will learn from labeled data. So images paired with their correct labels. If you are giving a dog image, you need to label it dog. Cat image, you need to label it as cat. Okay, the data set. Again, what is the first step in any algorithm before predicting it? Preparing the data. Okay, let me zoom out, I guess. Okay, what is the first step? Prepare data. Collect a large data set of labeled images. Each image is associated with a label indicating the correct category. So some images will be like something like this: a picture of cat labeled cat, picture of dog labeled dog, picture of bird labeled bird. Okay. Again, this is to train the model. Once you train the model, of course, you are not going to give a picture with a label. If that's the case, then what is the point of using neural network, right? So first you will train it. Once you think it is trained and it is ready, then you will give images without any labels, then it will predict it for you. So as prepare, okay, I don't know why it converted that to text. Once we have that preparing our data, second step is we do some pre-processing. Previously with LDA, what did we do? Oh, come on, don't try to convert my, let's see. In our previous example of LDA algorithm, we kind of did, what is it, stemming? Similarly here, we do some pre-processing, like for example, like resizing. You standardize the size of all images. Oh my God. For example, like you want to resize all images to some pixels, but you will standardize to ensure uniform input to the network. Okay, I disabled that setting. Now I think we should be fine. So pre-processing, what is pre-processing? You are resizing the data so that all pictures are uniform. Then you do normalization. Okay, what is normalization though? You will scale the pixel values typically between 0 and 255 to a range between 0 and 1 to improve the network's efficiency. So that is part of preparing data, right? Let's say data, preparing data. Then next step is to build our neural network. And what did we discuss? It contains, the first one is input layer, or you can say input layer. This receives the pixel data of the image. If the image is 224 by 224 pixels with 3 color channels, right? RGB. Now, how many neurons it will have? 224 times 224 times 3. So total it will be around 150, 528. So it will contain this many neurons. Okay. Which one? The input layer. Then you will have hidden layers, not just one layer. Hidden layers can be many layers depending on what kind of thing you are trying to do. So here, this is image classification. So one hidden layer will be something called convolutional layer. It is an optional, but it is a common layer that you will see. What does this do? These layers are typically used in image classification tasks to detect features like edges, textures, and shapes in the image. That's why you will use convolutional. And this is what? For image classification. If you are doing regression or something else, then you might not be even using this one. So what does this do? This detects features. Okay. And then another hidden layer might be fully connected layers. After the convolutional layers, fully connected layers will process the extracted features. These layers consist of neurons that are connected to all neurons in the previous layer, allowing the network to combine the features learned by the convolutional layer. So let me show you a picture so that it will be easy to understand. Something like this, as you can see, right? So this is our input layer, and then hidden layer you can think of like convolutional layer or something like that, and then the fully connected layers, correct? So these again is going to consist neurons that are connected to all the neurons in the previous layer. This is the previous layer, or this is the previous layer. It's connected, all connected, allowing the network to combine the features learned by the convolutional layers. So once that is done, what are we going to have? Remember, we are going to have something called activation functions, right? The activation functions. Now each neuron applies this activation functions, and one of the example I said is ReLU, to introduce non-linearity, enabling the network to learn complex patterns. So these all things, convolutional layer, fully connected layer, activation happens in hidden layers. And once that is done, then we are going to have output layer. This consists of one neuron per class. Example, three neurons for the classes. For example, what do we have? We have cat, dog, bird, three classes. So we will have how many neurons? Three neurons in output layer. And in the input layer, pixels times the RGB, that many, but here you will only have this many. And then you have something called softmax activation. In the output layer, a softmax activation function is applied, similarly like in hidden layer activation function, and here you will have softmax activation function. This will convert the raw output scores, which you will call logits, into probabilities. The neuron with the highest probability determines the predicted class. Okay, so that's all that. Now you need to train the neural network. Okay, let's train the neural network. What did we learn? Forward propagation. The image is passed through the network layer by layer. Each neuron processes the input it receives, applies its weight and bias, passes it through activation function, sends the result to the next layer. The example here would be the network might detect edges in the first convolutional layer, then combine edges into shapes in subsequent layers, and it finally recognize the entire animal in the fully connected layers. And then you have, this is forward propagation, then you have loss calculation. After the network makes a prediction, the loss function, example of a loss function would be cross entropy loss. It compares the predicted output with the true label to measure how far off the prediction is, right? Let's assume that you have a cat, but it identified as a bird. That is like too much error, right? So then it knows it has to reduce the loss. At least cat should look something like maybe uh, cat example, another cat example, maybe a wild cat or a cheetah or at least something like that. Then you have the backward propagation. The network uses the loss to adjust the weights and bias through back propagation. This process minimizes the loss by updating the weights in the direction that reduces the error using an optimization algorithm like SGD. This is an optimization algorithm. We will have a specific video just for this one. This is called stochastic gradient descent. And then how long? You already know epochs. The network is trained over multiple epochs, with each epoch consisting of several iterations. In each iteration, a batch of images is passed through the network and the weights are updated. And then you will evaluate the model. The performance of the network is evaluated using metrics like accuracy, which measures the percentage of correctly classified images in the validation set, and the network's predictions are compared with the true labels of a separate validation data set to assess how well the model generalizes to new data. Once you evaluate, finally you will start making predictions. Once trained, the network can classify new images it has never seen before. For example, if you provide a new image of a dog, the network processes the image through its layers and predicts the class dog with a high probability. This trained model can be deployed in various applications such as a photo organizer that automatically tags images by the type of animal they contain, or a security system that detects animals in camera footage. Okay, so that's one example, but since neural networks is an important topic, I have another example with me to talk about. Imagine we have a data set of images and our goal is to classify them into different categories. So what are those images we have? Let's assume we have images of handwritten digits, which is a common task in image classification, by the way. So the images looks like something like this. Okay, these are the images, and if you see, each image is labeled a number. This is 5, this is 0, this is 4. Even though all these pictures look same, assume that these images are different, and then they are labeled with numbers. So each image is 28 by 28 pixel grayscale images of handwritten digits, and they are labeled between 0 to 9. You can only see 5, 0, 4, but imagine there are more pictures and they are labeled between these numbers. Now, what will we do first, right? Each of these is flattened into a one-dimensional array of, when you multiply that, you will get what? 784 pixels. Okay. This array is the input to the neural network. So for the image of digit 5, how many pixels we will have? From pixel 1 till 0 to 255, remember? 0 is black and 255 is white. Now the flattened input is passed through a series of hidden layers, because this one pixels already went to the input layer that we discussed. Okay, and then from there it will be passed through a series of hidden layers where each neuron in a layer is connected to every neuron in the previous layer, that we have already seen in this particular image. These connections have weights that are learned during training, that we already found out. Now, if I only can okay here. If we have a hidden layer with, let's say, 128 neurons, each neuron receives input from all 784 pixels. So you have 128, each one receives 784 pixels. And then it will calculate the weights for each one of them. Again, the weights will it keeps on adjusting every iteration. Okay, so the weight table might look something like this. Okay, so if you see the input neuron, pixel 1, pixel 2, pixel 784, each neuron gets all 784 pixels. Now you have hidden neuron 1, and that weight there, it might be calculating this much, and hidden neuron 2, it might be calculating the weight this much, and then another hidden neuron 128, because we said there are 128 neurons, so it will so on and so forth, and that much. So this is how a weight table might look like for you on each neuron. Then in the hidden, what happens? We have convolutional, and then we have what? Um, Activation function, correct? After calculating the weighted sum of inputs, activation function like ReLU is applied to introduce nonlinearity, allowing the network to learn complex patterns. So how do you do that? Of course, it will have a function. It will have some function like max of OX. This function outputs 0 if the input is negative, and the input itself if it's positive. For example, this is negative, so it will output as 0. This is positive, so it will output 0.2. And after these calculations, then we are ended up in the output. Let's go here again. We are ended up in the output layer, which is the final layer, which typically has as many neurons as classes. And remember, we labeled the images from what? 0 to 9 are not labeled, but we in the images, what do we have? We have digits 0 to 9. So total 10 digits, correct? So we will have in the output 10 neurons. Each neuron outputs a probability that the input image belongs to a specific class. Okay, so the output would something look like this. The highest probability indicates the predicted class. In this example, the network predicts the image as digit 9. In forward propagation, because I mean this is so far done, and then now it comes to training the network, and then we have the forward propagation. The input image passes through the network layer by layer until it reaches, we already know that. Then the loss function, for example, if the true label is 5 but the network predicts 9, the loss function will calculate a high loss value, correct? Because you predicted 5 as 9. So the backward propagation calculates the gradient of the loss with respect to each weight in the network. These gradients are then used to update the weights, reducing the loss. So after the back propagation, we have evaluating the model and then visualizing the process. So if you have to visualize the process, remember you have input layer 784 neurons, then hidden layer 1 128, hidden layer 2, and then finally the output layer 10. If you have to look at the training process graph, this is how it looks like. After evaluating, you might create a confusion matrix to see how well the model performs on the class. And the confusion matrix might look like this. So whatever you are seeing here, this is true and this is the predicted value. True means whatever we know by looking at them, we know that it is 0, 1 or something, and this is the predicted. So this is how it looks like. So it predicted 0 as 0, 98%, and it predicted 0 as 8, 1%, and 5, 1%. And 1, it predicted as 197%, and you can see that. And the number 9, it predicted 98% 9, and something else might be 2%. So this is how it looks like. So the conclusion, neural networks learn to classify images by adjusting weights through a process of forward propagation, backward propagation, and optimization. Over time, the network improves its ability to recognize patterns in the data, leading to accurate predictions. By visualizing the structure and training process, you can better understand how neural networks work in tasks like image classification. That's about it. No more examples. I hope you enjoyed this. If you at least learned 10% what neural network is, and if my explanation helped you with that, then do let me know in the comments, so that other people who wants to watch this video, they look at the comments and be like, oh, it is helping, then they will watch it. That's how they do that. That's the reason I ask you to comment all the time. When you like and comment, one thing is the YouTube top 5 search list, our video will be shown. Another thing is people come and check the comments first, and they will be like, is this video any good to spend our time on? So that's why comment saying whatever it is, positive or negative, doesn't matter. If it is negative, then people won't come and watch. That's fine with me. But just comment what you think of the video. So don't forget about it, commenting. Thank you very much for spending your time here. See you in the next video. Have a nice day. Peace out.